last time we did Kirchhoff's voltage law, Kirchhoff's current law, and we worked out the essential differential voltage for a strain gauge. So today I just want to go through what they call the superposition theorem. So if you have a network, let's assume a DC network, because we're not going to do AC superposition theorem today where you need the phasors and stuff. So we're going to start off with the normal DC superposition. In the superposition theorem, you basically short circuit the voltage sources. So we're gonna end up with a circuit looking like this one will normally be asked. So like the circuit over here, we have two voltage sources. They have different polarities facing different directions. For instance, top bus will receive a positive voltage from the one source and essentially a negative voltage from this side, right? So that is going to play into the current flow. Short circuit the voltage source and only look at one voltage source at a time, which is going to be this 10 volts. Dead shorted the other source. We know for a fact that this 3 ohm is in parallel with these two, and there's only a 2 branch with a 5 ohm and a 2 ohm, and so it's the 2 multiplied by the 5 divided by the 2 plus the 5, and this essentially will give you your equivalent parallel resistance. You add that to the 3 and you end up with 4.429 ohms. All right, total amperage pulled by the resistances. Voltage divided by the total resistance. That'll be the total current that that source will provide. So it ends up being 2.258 amps. So IT is flowing through the 3 ohm. The problem is how much will branch up into what we're calling I2, which is essentially what we're going to be calculating because we're going to call that 5 ohm the load. How much is going into each individual branch? So I2 is essentially the one with the 5 ohm. So it splits via I total multiplied with a 2 ohm over the total ohmage of each and individual path, right? Yes, I1 is essentially the current going through the 2 ohm resistor. That's I total multiplied by 5 over 7. So what you go and do is you repeat exactly the same calculation, but now with the 20 volts, which has its polarity opposite to the 10 volts. So now we're going to take it from negative to positive, which is actually the way electrons flow. It's got this 2 ohm in series with it, so we can see its total resistance will be the series plus the parallel. We've already gone through this. Which equates to 2 plus 15 over 8 equals 3.875 ohms. The total current will be the total voltage, which is 20 volts, divided by RT, which is the total resistance seen by that 20 volt source, right? Which adds up to 5.161 amps. Right, and the same thing applies. We know that 5.161 amps will essentially be flowing through the 2 ohm, the total, because IT will flow through that. It's in series ohm, but we're looking at the branch resistances, right? How is it going to split there? And the answer is kind of indirectly proportionate to resistance. Correct. So 8 over here is the total resistance. It's 5 plus the 3 over here gives you the 8, right? What we get to is I2 is equated to, so I2 is the one running through the 5 ohm, is 3 over 8 multiplied by IT, 1.935 amps. I1 is essentially 5 over 8 equals 3.226 amps, right? So now we have I1, I2, and I1 and I2 for both the scenarios. So what we do is we superimpose them on each other. I2 in the top situation, and it flows up. So what that means is we have to subtract the larger value from the smaller value. Second calculation, I2 was flowing down, and in our first calculation, I2 was flowing up. So we subtract them from each other, and we get a superimposed value of 1.29 amps. Do the basics you need for circuit analysis.